Okay, cool. So this is the very last lecture in scope for the midterm. Now we know it's like a couple days before, so you're not expected to know this stuff for the midterm in a lot of detail. Honestly, as long as you watch through this lecture or read the corresponding readings, like you'll be okay. We're not testing any of this in great detail, but it's still good to know. Okay. So just to quickly review from last time, and I guess if we have time left over at the end, we could also go back and talk about digital signatures in more detail. But last time we talked about public key encryption, and the idea was that everybody uses the public key to encrypt, one person uses the private key to decrypt. We talked about hybrid encryption, which was a solution to the fact that encrypting things with public key, it can be slow because it uses all this magic math, and it can also have size limits. If you're doing things like mod p or mod m, then the messages that you can encrypt, they're between 0 and p-1, 0 and m-1, because you're limited to this mod space. So if I want to encrypt two messages that are equivalent mod m, the decryption will not be clear. So we have to encrypt things within size limits. So it's all kind of annoying. And the way that we fixed it is that instead of encrypting our message directly, we added this layer of indirection. So we use public key, which is great because people don't have to share a key. We use public key encryption to just encrypt the symmetric key, send that to the other person. Now the other person has the symmetric key they can decrypt. And now, thanks to public key encryption, both sides have a key that they share. And now they can use fast symmetric key cryptography, where all we have to do is shift a bunch of bits around. Okay, and then finally, we talked about digital signatures. So here the idea was that only the person with the private key can sign something. So if I own the private key, I'm the only person in the world that can sign things with that private key, but everybody else in the world can use their public keys to verify. And we saw one possible implementation, which was also based on RSA. And so here the idea was that if you remember all the way back to RSA encryption, the way that we encrypted was we took the message, you raised it up to the E power, and then how do you decrypt? You raised it up to the D power, and the E and the D, they cancel out, they're multiplicative inverses. But in RSA signatures, we go in the other direction. So when we want to sign something, we first raise the message up to the D power. That creates a signature. And we hope that nobody else can raise things up to the D power because they don't know the private key. And how do you verify? Well, you take that M to the D, you raise it up to the E power, which is the public key. So everyone can raise something up to the E power. And if the result comes back as M, then you know that the signature is verified. Otherwise, it's not. So that's the high level idea. It is just RSA encryption, but instead of raising something to the E for encryption and then D for decryption, you raise it to the D first to sign. Everyone else raises to the E to verify. Short summary of last time. Okay, anything else you want to know about stuff from last time? Okay. So we're actually at the very end of cryptography, believe it or not. So all I have to do today is wrap up a couple loose ends throughout things that we've done. So couple topics, certificates, and password hashing that are more involved. And then at the end, if we have time, I have all these random case studies. If we have time, we'll get through them. If we don't have time, you can read them on your own, but that's today. Okay. So the first problem that we have to solve, we solve all these major problems. We've gotten all the way to public key cryptography, but there is one problem. So first, I guess we can talk about what makes public key cryptography so great. Well, what's amazing, this is a thing that was not possible like 50 years ago or whatever, but what's really amazing is that now two people can communicate securely, even if they don't share a secret. That's pretty cool. And we took all of this math to unlock it, but it's a pretty cool achievement. I can sign something, you can all verify, and nobody can forge. I can also encrypt things and only you can decrypt. That's all great. We don't have to share any secrets. So is that like too good to be true? Like, how can this be possible? Are there any catches? So there is one catch, and maybe you've already spotted it, but it's kind of subtle. And so the catch is that public keys are kind of hard to distribute. So, well, what do I mean by that? So suppose Alice wants to send a message to Bob. It's our classic scenario. We've seen it over and over again. And so what's the first step that we saw in all of those public key encryption protocols? Well, the first thing is that Bob publishes his public key to the world. He generates the key pair, and then he announces to the world, I am Bob, this is my public key. Another way of saying it is you could say Alice asks Bob, hey, what's your public key? And Bob answers. These are basically equivalent, but somehow Bob has to send his public key to Alice, either by publishing it to the world or by sending it to Alice. Okay, and then after Bob has sent his public key to Alice, now we can do all the public key stuff where Alice encrypts with the public key or signs something and Bob can decrypt and verify. So that's all great. But this step where Alice asks Bob for his public key or where Bob announces his public key to the world, that part is actually kind of vulnerable if you think about it. Like think about Mallory looking at this scenario. So it's true that once we get to the stage where Alice is encrypting things and signing things, it's kind of hopeless for Mallory. She can't tamper with things, she can't read things. But what about that very first step where Alice asks Bob for his public key? Could Mallory do something there? Well, maybe what she could do is she's the man in the middle. She can modify messages. So when Bob announces to the world or when Bob sends to Alice, I am Bob and here's my public key, Mallory could take that message and say, I don't like this message. I'm going to take this message, tamper with it, and I'm going to replace Bob's public key with like my public key or something. So now Alice believes that Mallory's public key belongs to Bob. Well, that's kind of bad because now if Alice tries to encrypt the message with the key that Bob provided, that Mallory tampered with, suddenly Alice is encrypting the message with Mallory's public key, and Mallory could use her own private key to decrypt it. So that's the problem. The problem is it all looks so beautiful and perfect, but if you squint a little bit, there's this really subtle edge case, which is that very first step where the public key is announced to the world or distributed to other people. Someone could tamper with that. They could send their own public key. They could send someone else's public key. So that's a problem. We have to solve that today. Okay, that's a picture version of it. Bob wants to send his public key to the world, but Mallory intercepts it and says, I don't like that. I'm going to change it. I'm going to make Alice receive my own public key. So Alice receives this key, but she thinks that it's from Bob. So when she sees this, she thinks that this is Bob's public key. So she encrypts it with what she thinks is Bob's public key, sends it to Bob. Mallory can decrypt it. She can maybe even tamper with it before sending it forward to Bob. So we have a problem. We have to solve this. Okay. So how do we solve it? Well, maybe your first instinct and my first instinct might be, well, we already designed signatures, didn't we? Wasn't that the whole point of signatures, is that when I have digital signatures, someone cannot tamper with the message. Like if I sign a message and you tamper with the message, then the signature will fail to check out. If I have a message and a signature and I tamper with the signature will fail to check out. If I try to tamper with both, I cannot forge a message with a valid signature. So at first glance, it seems like, wait a minute, I can just use signatures to take care of this, right? But think about whose private key would I be using to sign this? So when Bob publishes his public key to the world, who's signing it? Well, I'd imagine Bob's going to be the one to sign it. He's sending this thing to Alice. He is publishing the key to the world. So I guess Bob signs it. Okay, so Bob uses his private key to sign his public key. That's great. How do I verify the signature? I have to use Bob's public key, but that was the thing I was trying to verify in the first place. So how am I getting that? So we run into kind of like a circular problem. If I want to make sure that Bob's public key is correct and untampered with, I could try to sign it with Bob's private key. That's the person sending it. But how do I verify the signature? I use Bob's public key, which was the thing I was trying to verify. It kind of like melts your brain, but it's a circular problem. Basically, the problem here is that the thing we're trying to verify is the thing we need to use to verify. So it seems like we're kind of stuck. So somehow, I don't know how to send this public key to Alice in a trustworthy way. Bob can't sign it himself because this is the thing I used to verify. So you kind of get stuck. Okay, so another way of putting this, and this kind of gets a bit more philosophical. The problem here is that Alice doesn't trust like anybody. If she only trusts things that are signed, she starts trusting nobody. And if you go through life trusting nobody, then, well, you're going to kind of have a sad time. So somehow we might just have to put our trust in somebody and then use that trust to gain more trust. I realize that's like super deep and philosophical, but we'll see what it looks like in the context of distributing public keys. Okay, so the goal here is that, yeah, there's this problem of, this is true for Bob, it's true for anyone that I talk to. If I want their public key, I don't have a way to get the public key. They can't sign it because then I can't really verify it. So ultimately, I need to pick someone that I trust and then like listen to what they have to say and hope that that helps. Okay, so that's what the trust anchor is, and we'll see it really soon. Okay, this is a little bit of like off topic, I guess, before we go into the actual meat of certificates. But one protocol that you'll see sometimes, and this is not the approach that we're going to talk about today, but another approach that you might see out there, it's called trust on first use. It's kind of clever. And so the idea here is that the first time that Bob sends his public key, it is true that you don't know, is it Bob's public key? Is it Mallory's public key? Like you don't know, it could be anyone's public key. So the first time that Bob sends his public key, you're not really sure whether it's his or whether somebody else tampered with it. So one thing you can do, and one thing that a lot of real life protocols like SSH do, is they'll tell you, this is a public key that you have never seen before. You don't know who it belongs to. It could be Bob, it could be Mallory. So do you want to trust this public key? And if you trust it, then I'm going to save it. And in the future, I will believe that this belongs to Bob. Otherwise, if you don't trust it, then we're not going to use this key. So if you've ever used SSH and you get those like warnings like, hey, do you want to proceed like on project 1 or whatever, what were they actually asking? They were asking, you're trying to use the public key of this other computer, like the Hive machines or whatever. And they were asking you, do you trust this public key? Because I do not have a way to trust public keys at the moment. So can you just implicitly trust it? Do you believe that this is the real public key? And if you typed yes, then your computer trusted you and said, okay, I'll take your word for it. That's actually their public key, even though I wasn't sure or I don't have any cryptographic proof. So here, what you're relying on is you're just kind of hoping that at the moment you're not being attacked because attacks don't happen too often. So you are taking a bit of a leap of faith. You're hoping that the first time that you log in, no one is attacking you. But depending on your threat model, maybe this isn't good enough, or maybe it is. So if you believe that like this, EEC servers are not out there attacking you, then maybe this is good enough. But if you're working for, national security organization or something, maybe this isn't good enough. So this is one possible approach, is just to trust on first use and then in the future, trust that public key going forward. But we're going to look for something a little bit stronger than this, but do know that some protocols, they go with this. Okay, so the thing that's a little bit stronger that we're going to use is something called certificates. And like, I'm not a huge fan of this name. And someone asked in chat, how do you verify that a public key belongs to someone? So this is what a certificate's going to do. So I'm not a huge fan of the name certificates. Like, it doesn't really tell you what's going on. Like when I see public key encryption, I'm like, oh, I know what this is. It's using public keys to encrypt. But when I see the word certificate, I'm like, I don't know what this is. So don't get tripped up by the word and think that certificates are this huge, complicated thing, or it's doing more than it claims to do. A certificate is just some fancy word of a really like simple, relatively speaking, cryptographic value. So what is the value that we call a certificate? It is only this, which is it is your public key signed by someone else. That is it. There's nothing else to the certificate. Does the certificate involve like a message or like person or whatever? Nothing, right? All that a certificate is it's a message saying something like, this is Bob's public key, signed Alice, or something like that. That's all. So it says, this is Bob, this is his public key, and there's a signature on it. That's all that a certificate is. It's someone's public key signed by someone else. So yes, the name is kind of weird. If I wanted to name it, I might call it something like public key signed by someone else, but I didn't name these. So we're stuck with certificates. Okay. Sometimes you might see them written using like shorthand like this, but the important thing is, what is a certificate? It's a message saying, this person is Bob and their public key is this. And we take that entire message, we sign it, we send the message and the signature, and that whole value, the message and the signature, it is the certificate. So the idea here, like why certificates are even useful, is because we already saw that problem from before, which is Bob cannot convince Alice to trust his own public key. So instead, Bob is going to say something like, okay, maybe you don't trust me because I have no way to verify my public key. So you'll never know if I am who I claim I am. But suppose that Alice has a friend like Evanbot. Everyone's friends with Evanbot. So maybe if Alice trusts Evanbot, and what we mean by trust here is that Alice and Evanbot are friends, Alice knows exactly what Evanbot's public key is, then here we can say Evanbot is our trust anchor. This is someone that we trust no matter what. We know what their public key is, we trust them. And how do I know what their public key is? Well, maybe I just trust them and hope that I wasn't attacked or something. But somehow, this is someone that I trusted. How did I trust them? That's up to your protocol. But the important thing is that we trust this person. We believe that this is truly their public key. So if the person that we trust sends us a certificate saying Bob's public key is this, and they sign the message, it's signed by someone that you trust, then you have basically taken your trust in that person, and you're using that trust to spread the trust out to Bob. So that might be kind of a confusing way of saying it. But another way of saying it is, if I trust Evanbot and Evanbot says that Bob, that's his public key, then I should probably trust that that is actually Bob and that's his public key. So I trust what Evanbot says. We all trust what Evanbot says. He's our trust anchor. Okay. So what is a certificate? Such a fancy name, but all that it is, it's a message saying something like Bob's public key is blank and a signature on that message by somebody else. That is all that a certificate is. What is a certificate good for? A certificate is good because if you cannot verify your own identity, you could ask someone else that you trust, like a third person. And if I trust EvanBot and EvanBot says, yes, Bob's public key is this, here is a signature on that message to prove that I sent it, I can use EvanBot's trusted public key to verify that. Now I trust Bob. And this can actually go on. So now that you trust Bob, maybe Bob can endorse somebody else, and that person could endorse someone else. So certificates can chain together, which we'll see. But how does a single certificate work? It's nothing more than a message and a signature on it. Okay, so that is the definition of a certificate. So now there's a question of, okay, so I kind of know how this works. If you trust someone, you can delegate that trust or spread that trust to someone else. But there is still a question of where did these things come from? Like who generates certificates in real life? So we could organize certificates in a bunch of different ways. So here's one possible way. So we could say, maybe there is one person that everybody trusts. So like everybody in the world puts their trust in like one trusted directory. So this is like the most trustworthy person in the universe. And we delegate them and we say, it is your job to tell me what other people's public key is. Everybody in the world trusts you. We're counting on you. And you're going to tell us what everyone else's public key is. So that's our trusted directory. It's a single person in the world, the most trustworthy person in the world, and they're going to tell us what everyone else's public key is. So how does this work? Well, we could have this single most trusted person in the world. They can have a public-private key pair. They can send it to everyone else in the world, and everyone else is going to believe that this is the right public key. Why do they believe that this is the right public key? Because this is the person that we are implicitly trusting. We're like, we trust you. We hope you're trustworthy. And so we all hope that everyone uses, or everyone believes that this is the trusted directory's public key. So everyone trusts this. Like we'll bake this value into our computers, our phones. Everyone knows this value. We all trust this person. So if everyone trusts this person, then now anytime I want to know someone else's public key, like, hey, what's Bob's public key? I go up to the most trusted person in the universe and I say, hey, what's Bob's public key? And the most trusted person in the universe sends me a certificate. What does the certificate say? It says, Bob's public key is this, signed by that really trustworthy person. And I can use that really trustworthy person's public key, which I trust implicitly, to verify the certificate. There's the message. It's signed by the trusted key's private, or the trusted directory's private key, and I can use their public key to verify. So now this person can tell me everyone else in the world's public key. Okay, that is one possible approach. So in this approach, who are we putting our implicit trust in? So remember, if we trust nobody, if we go through life trusting nobody, then we're never going to be able to believe Bob when he says something too paranoid. So we have to invest our trust in somebody first, and then they can spread the trust to other people. So in this case, who is the person that we are just believing blindly without taking their word for it? In this case, the person that we are believing blindly is the trusted directory. That's the one and only person who we've put our blind trust in, and they are going to delegate trust to everybody else. Okay. So we trust that person. We trust that this is correctly and truly their public key. And then we also trust that they're a trustworthy person and that they will only sign certificates if the person is trustworthy. So I said the word trust a lot, but it's a lecture about trust. So talking about that. Okay. So that's one possible approach. And maybe you already don't like it. So let's think about maybe why we don't like it. I guess we can show an example first and then talk about why we might not like it. Okay. So one reason why we might not like it is because, I guess here's our example, which is that the trusted directory is like the president of UC, right? This person is probably pretty important and trustworthy, I'd say. I don't know this guy, but maybe he's really trustworthy. This person is our trusted directory in all of the UC system. So in this case, if I want people's public key, I'm always going to go up to this one person and ask them. So I want Nick Weaver's public key. He used to teach this class. I'd go up to the trusted directory and ask. I want David Wagner's public key, guy who invented the block cipher. I would go to Michael Drake and ask, and so forth. Okay, so maybe you already don't like this scheme. And what are some reasons why you might not like it? Well, one reason is like this person is probably going to be very busy. Like if we delegate one person in the world who we trust, and their job is to provide public keys to everyone else in the world, that's kind of a lot of work to put on a single person. Who's going to do that? How do we put all of our trust in a single person? So there's one problem, which is this person is probably just not going to have the time, or even if we thought about like some server that's doing this server is probably not going to have enough compute power to serve the entire world and give certificates to everybody in the world who requests. So this approach, it's not scalable. Maybe like in a small club or something where you trust the president, maybe it's good enough. But like for the whole world, this is not going to scale well. And the second problem is like, well, what if this person turns out to not be trustworthy for some reason? Like, you know, maybe they're walking in, like they drop their keys somewhere and someone else picks it up. Well, suddenly all of the trust that the entire world put into this person, it's like misplaced now because this person is no longer trustworthy. So there's a single point of failure. And if this person fails, it's going to affect the entire world. It's like catastrophic because now everyone was relying on their trust on this person. And if this person is no longer trustworthy, then, well, things are going to start to break. Everything's going to start to break. I no longer know whose public key is whose. Like someone sends me their public key, I don't know who that person is. So I'm going to have problems. Okay. And another problem in terms of like scalability and usability is like, imagine this person or this server like goes down for a minute. So server breaks or something, someone has to come fix it. Well, now the entire world has to wait for this server to come back up. Also kind of a problem. So it was a nice approach, but turns out having a single authority or a single point of failure, it's not good for scaling. Okay, but it was a nice try. And in theory, it would work if there was someone this trustworthy out there. Okay, so let's try again. And this time, let's think about, well, what would this look like in real life? So in real life, there's no such thing as we walk up to the most trustworthy person in the world and ask them to do all this work for us. So instead, let's think about what this might look like in real life. And so in real life, we might do something a little bit more scalable. And in particular, I guess I'll pull it all up. We're going to do something like building a tree of trust. We're going to say, let's not just have one person endorse everybody. Let's try having one person use certificates to endorse these people, and all of these people can use their keys to endorse these people. And all of those people can use their keys to endorse more people. And so the trust can start at a certain person, and it can slowly spread all the way out. So instead of one person being responsible for all of the work of giving certificates to everyone, they can delegate trust to more people. Those people can also delegate trust to more people. So I can have this big, slow spread of the trust. Okay. So for example, here, I'm going to build a hierarchy, and it's still going to start with like Michael Drake, the actual UC guy. I actually don't know. Like, has he been like fired or canceled or something recently? Is that still the guy? I don't know. These slides are kind of old. Okay, we'll look it up together afterwards. I think I looked it up a year ago and it still was, but you never know. Okay, so Michael Drake, like the guy, this is the guy at the very top. And so the first thing I'm going to do is Michael Drake, this guy's probably pretty busy, probably does not have time to sign public keys for every single person in the UC system. It's like, what, tens of thousands of us. There's just no way, too busy. So maybe what this person will do is Michael Drake is going to, instead of delegating trust to each individual person in the UC system, he's going to use a certificate to delegate trust to people at like each college. So we could say, okay, Carol Christ, I don't know, but I think, is she still UC Berkeley chancellor, or is she like gone now? I don't know. She retired? About to retire? Okay, so this slide is still good for today. All right. So we could say, instead of delegating trust to every single person, Michael Drake will delegate trust to only Carol Christ. And so how do you delegate trust? The way that we delegate trust is we use a certificate. And what is a certificate? It is nothing more than a message saying, here's Carol, here's her public key, I trust her, signed Michael Drake. That's it, that's the whole certificate. And using the certificate, anyone who receives the certificate now knows, if I trusted Michael Drake, and Michael Drake told me that Carol's trustworthy, then I probably trust Carol now as well. So it took the trust from one person, spread it to a second person. Maybe Michael can spread it to all of the individual UC campuses. I do not know the chancellor names at other UC campuses, but we can imagine they all get similar certificates. Okay, and so we can keep doing this like step by step. So we could say, okay, Carol, you're going to sign, or you could sign the public keys of every single person on the Berkeley campus, but that's a lot of people. So maybe she delegates like by department or something. And again, how do you delegate? all you have to do to delegate trust is to send a certificate. And what is a certificate? It would just say something like David Wagner's public key is this, and I trust him to sign for the CS department. So it's the name of the person and their public key. I sign it. So now anybody who trusts Carol, they now trust David. So that would be the second layer. And we can do this over and over again. I think when we made this slide, Dave Wagner was the CS chair. So I don't know if he still is. I don't think he is, but that was the intent of this slide. Okay. And so this can keep going layer by layer. How many layers you do is kind of up to you and how you want to organize your organization. But that's the idea. Instead of having one person sign everybody's public key, we can have hierarchical certificates where person A delegates trust to person B delegates trust to person C. And the way that I would do this is I would come up with all of these different certificates, and each certificate says nothing more than this is a person that I trust. If you trust me, now you trust them. And we can do that over and over again to spread trust out. And a really common way that we would draw these is we draw a tree like before. Someone at the top, they delegate, they delegate, they delegate all the way down. Okay. So once we build something like a tree, we get all these fancy names, but these are just names for the thing that we just saw. So if that made sense, I'm just adding a little bit of vocabulary. So that person at the top, like Michael Drake guy, we sometimes call them the root certificate authority. And here, I guess the intuition is that's like the root of the tree. It's at the very, very top. But sometimes we call them a certificate authority. This is a person who is an expert at certificates. They can generate certificates for other people. And sometimes we also say this for the people in between. So like Carol Christ, who is delegating trust, and like David Wagner, who is delegating trust. Sometimes we call them intermediate certificate authorities. So here, a certificate authority is just a fancy way of saying this is a person who's going to generate certificates for other people. So if you trust them, you can ask them questions and they can delegate trust using certificates that they generate to other people. Okay, so that is maybe how you would do it in like this, fictional UC example. In real life, what does this actually look like? That's a good question. And it turns out with security, sometimes we're going to like bridge the gap between cryptographic protocols that are like pure math and things that actually happen in the real world, which I think is pretty cool. And so this is one of those cases where, what does this actually look like in real life? Well, we can't just have a single root in real life. Who is this most trustworthy person? So instead, what actually happens, and you can look this up afterwards if you want, is there are like around the order of 100 root certificate authorities, and each of them have like their own tree where they delegate trust to all sorts of different people. And so if you look at like your internet browser or something, you'll see that like Firefox or Chrome or whatever, they come pre-bundled with the public key of like these 150 root certificate authorities. And we just assume that they're trusted, or Firefox assumes that they're trusted public keys. And how do we trust them? Well, I mean, that depends on you. If you don't trust them, you can go and delete them from your browser and suddenly you don't trust them. But Firefox, Chrome, like they generally believe they're trustworthy. And these are based on things like real life business relationships, organizational relationships. So for example, one of these could be like a big company, like Google might have a root certificate authority. And so now the question just becomes, do you trust Google? Like, is that a trustworthy company that you think is only going to sign legitimate or like delegate trust to legitimate parties, or is Google going to delegate trust to an attacker? I don't know. That depends on how much you trust, mega corporation Google or whatever, right? Or maybe say like the US government might have a root certificate authority. So, do you trust the US government to sign the public keys of other people and trust that the US government will not sign the public key of an attacker? I don't know. That's up to you. So that idea of like real world trust has to come from like business relationships, organizational relationships. It's kind of interesting. So that's what this bottom part talks about. Okay, cool. Questions? Yeah.
Do Google and the US government actually have root CAs?
Do Google and the US government actually have root CAs? I don't know. We'd have to look it up later. But I believe most root CAs come from some like organization, like nonprofits that deal with like the internet or companies like that. So it's a good question though. Okay, other questions. Certificates signed for students outside of UC Berkeley are not trusted. I'd say that depends. So like in this kind of silly example, we were assuming that David Wagner is only going to go through the trouble of signing public keys for Berkeley students and is not going to go through the trouble of signing other certificates. But if your model is different, it could only look different. There was a really good question, which is, can Mallory tamper with the certificate? I'm hoping there's a slide on it, but maybe not. So something kind of cool about certificates that I should briefly mention, even if there is no slide on it, is that certificates are public values. So think about what's in a certificate. In the certificate, I have somebody's name. I hope that's public. And someone's public key. Yeah, that's probably public. And a signature on those two values. All three of these things can be public. I'm not leaking any secret information when it comes to certificates. So certificates, it's okay. I can make them public, and that's okay. Something else that's kind of cool about certificates is that because they come with the signature, it doesn't actually matter who you get the certificate from. You can always verify whether or not the certificate is legitimate. So this might answer the question from before. So say, Mallory walks up to you, ooh, Mallory, and she hands you a certificate that says, this is Bob's public key signed by a certificate authority that I trust. So are you now suspicious? You're like, wait, but Mallory sent it. I can't trust Mallory. But remember, all the certificates come with a signature. So if you get a certificate, even if it comes from Mallory and it says something like Bob's public key is this, signed by EvanBot, you can still use EvanBot's trusted public key to make sure that this certificate that Mallory has handed to you is trustworthy. And can Mallory tamper with it? Well, she can try, but if she doesn't know EvanBot's private key, she has no hope of tampering with the certificate. So something else pretty cool about certificates is that they all have public values, and because they come built in with signatures, you can actually receive them from just about anywhere. You can always verify whether or not they're valid. So that's pretty cool. Okay. That's cool. Anything else I want to say about certificates? We're kind of getting into the trivia at this point, but a couple more things I guess I can say really quickly are that public keys are, for these root certificate authorities, they're usually hard-coded. So for example, when you download Firefox, it comes pre-built with a list of 150 public keys. And maybe you're concerned. You're like, how can I possibly trust those public keys? Like, how do I know that they're correct? But if you think about this, like these 150 public keys, like they're pretty much public knowledge. Like everyone knows them. Any of us with a download of Firefox will have these keys. So if you're super paranoid, you can also ask around and just make sure that these are the correct public keys. We're kind of getting into the weeds of things here, but you can almost think of these public keys as like common knowledge. It's like saying, who's the president of the US? Like, yes, Mallory could certainly come up to you and lie about who the president of the United States is, but like it's such public knowledge that getting the right answer is probably not going to be too hard. So I guess quick side note, if you don't trust the public keys of the root CAs, you could say there's such public information that the odds of me getting the wrong answer are pretty low. In the same way that it would be pretty hard to attack someone and convince them, that the president of the US is somebody else. Okay. I think that's mostly all I wanted to say. I guess one final thing I'll say is that you do not have to sign the certificates over and over again. So if you're a certificate authority, you can sign it, you can hold on to it with the message and the signature, like store it in your database. And whenever someone requests, you can just give it to them with the signature pre-signed. So you do not have to re-sign this thing over and over and over again as people ask for it. You can sign it a single time, hold on to it, and then distribute it whenever people ask for it. And that's nice because remember, signatures kind of expensive. So if I only have to do it once, store the signature forever and send it out, that's kind of nice. Okay, but I realized the last like 5 minutes, we got a little bit into the trivia of certificates. Most important thing is that they are someone's name, their public key, it is signed by someone that you trust, and I can use this to delegate trust in a hierarchical way. That's the important part. Okay, so really quickly, you might wonder what happens if certificate authorities mess up. So what if I accidentally send something that's wrong? So perhaps I got tricked or I got hacked or something, and suddenly there's a certificate floating around in the world that says this. It says Bob's public key is PKM, but PKM is Mallory's public key, and this message is signed. So anybody who trusts me, the certificate authority that issued this, is now going to believe that Bob's public key is that thing, that evil thing. So that is a problem and something that we have to solve. The certificate authorities, try to be secure, but sometimes this actually does happen once in a while. And it actually happened once where apparently they issued a certificate to someone that said like Microsoft's public key is this. And what was that? It was some random Joe's public key. So suddenly this person could now pretend to be Microsoft to everyone, probably bad. Okay. So how do you solve this? There's a couple solutions that people like to use in real life. So one solution is to make these certificates expire. And I kind of like this one. It's pretty simple. So the idea is that every certificate, in addition to the cryptographic values of like identity, public key, signature, they're also all going to come stamped with an expiration date. And so now anyone who receives the certificate will say, I'm only allowed to use this until the expiration date. after it expires, I'm going to re-request the certificate. Maybe the certificate that I re-request is the exact same. That's okay. But the expiration date forces me to check a couple times. So if someone hacks into my system and generates a bad certificate, or if I mess up and accidentally generate a Microsoft certificate to someone who is not Microsoft, well, yes, it's kind of bad, but it won't be too bad if the expiration date is short enough. Eventually, that bad certificate is going to stop being trusted by everyone else because it's expired. So that is one possible approach. Now you do have to start thinking about like, is this usable in the real life or like in real life? So now there's a bit of a trade-off, which is, well, I could make expiration dates really short. So this would be like, I give you, I don't know, do people still go to the library? You should, libraries are great. But like if you go to the library, imagine if they checked the book out to you and they said, this is due in 5 minutes. If you want it again, you gotta come back in 5 minutes, check it out again. So you read the book, you're on page 1, and then 5 minutes later, you go back and renew it. Page 2, go back and renew it. And like, yes, you can do that, but it's probably not going to be very, a good reading experience. So you could force the expiration dates to be extremely short. And in fact, this happens in real life. There are certificates that expire in like 5 minutes, 10 minutes, 1 hour. And what happens here is that you have to re-request a new certificate once every hour. So this is kind of unusable in some cases, more usable in others, because you have to keep requesting over and over. But the good news is that if something goes wrong, that certificate is going to become harmless in just an hour, or just 5 minutes. On the other hand, you could say, actually, these certificates renew once a year. So once you get a certificate, it's good for a year. Well, now the trade-off is that it's more usable in some senses because you don't have to go back and renew it over and over, but maybe it's less secure because if you get a bad one, suddenly it's floating out there for a year. Yeah, question?
If you renew certificates often, doesn't it decreases the number of certificates given and therefore increase the number of bad certificates?
Yeah, that's a good question, which is, would you increase the number of bad certificates if you were forced to redistribute over and over again? I guess it depends on what you're assuming the certificate authority is. If we think that they get hacked like 1% of the time, then yeah, maybe it's not a great assumption. But in general, we assume attacks are rare. So we're hoping that since attacks are pretty rare, if attack does happen, we want it to die off really quickly, like in an hour, as opposed to having the results of that attack like stay for years and years if the expiration date was really long. So that's our goal. Okay. There's a question of how do you verify the public key of a random old user? Like someone comes up to you and says, I want a certificate. How do they verify? That is actually between you and the certificate authority. So different certificate authorities will have different verification processes. Like in the real world, it could be something like, and I guess we'll talk about this more in the networking unit, but how would you know to issue a public key to someone? Sometimes the certificate authority issues like a challenge that only you can solve and you solve it, and then they issue a certificate to you, but that'll come up more in the networking unit. It's a good question though. And it's something that's up to the individual certificate authorities to enforce. So maybe a certificate authority could say something like, I don't think they do this, but they could say something like, you need to come in person and show me your ID and then I'll give you a certificate. They could do that too, but they usually don't. Okay. There is one case where frequent renewal could arguably be more usable. And we'll talk about that when we talk about Let's Encrypt, when we talk about TLS. So I'm not going to talk about it now, but it's there if you're curious. Okay. So approach number 1, a lot of small details, but the important thing is that we just use expiration dates, stamp every certificate with an expiration date. It creates a trade-off between usability and security, which we see a lot. Okay. There is a second approach, which is, I don't know, maybe you like it, maybe you don't. So the second approach is that every certificate authority will once in a while give a list to the world and say, okay, this is my list of mistakes. So I messed up here, 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 here. Please do not trust these certificates and delete them from your list of trusted certificates as soon as you can. And I will send another list next week of all of my mistakes. So in this case, I am repeatedly or periodically sending out a list of certificates that I do not like anymore. And sometimes people call that a certificate revocation list or whatever. But the important thing here is that the certificate or the certificate authority sends a list. They can even sign the list. And that way I can verify that the list is correct, delete all those certificates. Okay, so this also works totally fine. Lists can get large, maybe a potential drawback. I'd say the main drawback here, or a couple drawbacks, are like, well, first, now it's up to the user to actually like download these and make sure that they're revoking as they go. So maybe it's more work on the user. There could be a problem, which is like, what if the certificate authority is down? That could be a problem because now you don't know whether or not the certificates are expired or not expired or revoked or not revoked. So basically all of this is just to say that there are trade-offs between security and trade-offs between usability that we have to deal with. Okay, so certificates, revocation lists, expiration dates, ways to delete certificates we don't like anymore. Okay. One thing I'll briefly note is that we are only scratching the surface of certificates in the same way that we're only scratching the surface of a lot of these things. So yes, while it is true that like deep down a certificate really is just someone's public key and someone's name signed by someone else that you trust, there are a lot of specific things that go into it. So yes, it feels kind of simple, but I do not recommend going out and starting to implement this thing. There's like a huge protocol about it. So just be warned that we talked about it, but we only talked about the basics. Okay. So, I'm not going to talk about this too much, but there is another approach, which is instead of doing hierarchy like a tree, where that's the root person that I trust, they delegate trust to more people, they delegate trust to more people. You could also build it like a graph. And here we're building like a web of trust where everyone can sign for their friends and there is no like boss at the very top of the tree and there is no tree structure. So that also works. The main problem here is that it just gets super messy because these graphs can get super complicated. Like, oh, Alice's friend is Bob, and Bob's friend is Evan, and Evan's friend is David or whatever. So these webs of trust can get complicated. So people have tried it in the past, but they get a little bit annoying sometimes. Okay, so that's it for certificates. Again, the trickiest thing here, I honestly think, is the name, because seeing the name certificates does not remind you that all that it is a way for us to solve what was the ultimate problem that we solved. The problem that we do not know if this is really Bob's public key, and how do we know that this is truly Bob's public key? We ask someone else that we trust, and we can do that in this tree structure to get hierarchical trust. Okay, that's it for certificates. Okay, cool. So the second kind of final topic that we're going to briefly talk about, it's kind of like an application. So it's not really a hole we have to plug in our exploration of cryptography, but it is something that's pretty useful. So we're going to take some of our protocols and use them to build something that you might use a lot in real life, such as passwords. So I'm sure you know what passwords are. They come up all the time. So how do we store passwords securely? Well, I've kind of already given away the answer because it's called password hashing. But since I've given away the answer, I'll tell you a bit about cryptographic hashes. So remember that a cryptographic hash takes an arbitrary length input. You can pass in as long of an input as you want, and the output is going to look random. So if you change a single bit of the input, the output is unpredictable. We also know that the cryptographic hashes are generally pretty fast. They shift a lot of bits around. And we also know that cryptographic hashes are one-way and collision resistant. The important thing here is that if I show you a hash, you have no idea what input I use to generate the hash. You also cannot come up with any other input that matches to the same hash. They're also collision resistant. So if I challenge you, please find two hashes that output, or two values that output to the same hash, you're going to have no hope of doing that. Okay, so that's all hopefully in review. Okay, so now let's think about passwords. And yes, I have a definition of passwords on the slide if you really want it, but hopefully we all know passwords are that secret thing that you type in and it's like it's all circles when you type it in. Okay, so we know what a password is. Okay, so when you type in a password, have you ever wondered, like, how does the server actually know if my password is correct or not? So maybe the first thing that you think of is, well, maybe the server is just storing a list. Alice's password is this, and Bob's password is this, and Evan's password is this. So yeah, they could do that. Does that feel very secure to you? I don't know. It doesn't feel very secure to me, because imagine if someone hacks into their service or leaks information. Well, guess what? Now everybody knows your password, or the attacker knows your password. So if someone hacks into their system, they immediately learn everyone's password, and that's kind of bad news. So that's our first idea. We don't really like it. So now let's start thinking cryptographically. So maybe your first idea is, aha, I don't want the attacker to know what the passwords are. That sounds like a job for confidentiality. So perhaps what I will do is I will encrypt every user's password. And then when a user sends me their password, what do? I decrypt the password that I stored, check it against the password that the user provided, and see if they match. Does that work? Well, think about what happens when the attacker hacks into the system. What if the attacker steals the list of encrypted passwords and they steal the key? What happens now? We are back to where we started. The attacker still has everyone's passwords. So yes, we could encrypt every user's password, but this doesn't really stop an attacker. If they take total control of the system, they know the key, they know the encrypted values, they can simply decrypt and find out what my passwords are. So in real life, most people do not use approaches 1 or 2 unless they are really bad at designing websites. So instead, we want something a little bit trickier. Specifically, I want to be able to know that your password is correct. The user types a password. I want to know if the password is correct or not, but I do not want to actually store anything about your password. And you're like, wait, that sounds so contradictory. How can I verify that your password is correct, but not give the attacker any chance to know what the original password was? And like, how can that be possible? But remember, we have the power of hashing on our side. So instead of going with encryption or the passwords itself, let's store a hash of their password. And what's so great about this is, yes, we can verify that a password is correct. How do we verify? You send me a password, I hash the password that you sent, I check it against the hash of the password that I have stored. If they match, then you're good to go. If they don't match, then I do not log you in, your password is wrong. So when you first sign up, you give me a password and I hash it. I store only the hash. I don't store your actual password. And then every future time you log in, I rehash the thing that you send and I check it against the password hash. Like you can think about why does that actually work? Like what property of hashes am I using to back the fact that this is true? Like how do I prove that this will always work? I'm trying to think about it. Well, one thing that has to be true is this thing had better be deterministic, because if you want to sign in 10 different times, you're going to send me the password 10 different times. I'm going to hash it 10 different times. I'm going to compare it to the same hash in the file 10 different times. So I better be getting the same password hash over and over again if you give me the same password. Okay, so for usability purposes, it better be deterministic. And we know hashes are deterministic, so we should be okay. What else? Well, hopefully these things are one way. And why do we want them to be one way? Because again, imagine the attacker who hacks into my system. So what do they get? They get a whole list of these are all the users in my system and these are all of the hashed passwords that they have. So I do not want an attacker to be able to know if this is the password hash, like I've given them the password hash, what password did I use to generate the hash? I don't want them to know. And if the hash is one way, then I should be okay. So if I give them the hash, they have no idea what input I used to generate the hash, then I should be okay. Okay, so if we have those properties, then these hashes should be secure. So now users can log in and the attacker who steals my passwords file has no hope of knowing what the actual passwords are. Okay, but we're not like totally done, because even if the attacker doesn't know exactly what the password is, they might still be able to learn something about passwords. I don't want the attacker to learn anything about the user's passwords. So how can I do that? Well, imagine something like this. Maybe this is pretty common. So 2 users sign up and they both just use the super secret, top secret, 161 approved password, password 123. Think about what happens here. Both users use the same password. So what do? We store Alice has password hash of password 123. Bob has password hash of password 123. So what can the attacker do if they look at my file? Well, they'll notice, wait, Alice's password hash is this, and Bob's password hash is the same thing. And so the attacker can look at this and immediately determine Alice and Bob, even if I don't know exactly what their password is, they're probably using the same password because their password hashes are the same. So that's kind of the problem. So one problem is we are still leaking whether 2 people use the same password. Even if you don't know what the password is, I don't even want attackers to know that 2 people are using the same password. I don't want to leak that information. There's another problem, which is most people are pretty bad at choosing passwords. Like, I don't know about you, but not all of my passwords are like, really long, secure strings of random characters, right? Everyone loves to use like their birthday, their dog's name, whatever. And so what an attacker could do is they could use brute force to their advantage. So they could say, I know that most people choose passwords that look like stuff like this: password 123, password 1234, 123457990, the names of like all the common dog names, all like the birthdays out there. So the attacker could take all the common passwords that they know about using their domain knowledge of these are all the common passwords. They could simply hash every single one and then compare against the passwords file that they've stolen. And if they notice that, wait, when I hash password 123, it matches the thing associated with Alice, then Alice must be using password 123. Okay, what's this called? It's usually called a dictionary attack. And here the idea is that you take a dictionary of all the common passwords, or like maybe even a dictionary of all the common words that people use in their passwords. And I hash every single one by one by one by one by one. And then I check those against something in the passwords file. Okay. And it turns out if you do not want to calculate the hashes one by one by one, and you think it's too slow, there are actually algorithms out there that take advantage of the underlying way that hashes work to make it even easier to compute an entire dictionary of hashes in really fast time. Those are called rainbow tables. We're not going to talk about them, but they're pretty cool. They leverage the fact that hashes do like reuse work and stuff, so that if I want to hash the entire dictionary, there are more efficient ways to like hashing the first word, hashing the second word, hashing the third word. I can try to reuse work and hash the entire dictionary even faster. Okay. So these are problems. Basically, people can use the same password, and I don't want attackers to be able to brute force my passwords. So I'm going to solve both of these. So first, I'm going to solve that first problem, which is what if two different users decide to use the same password? So I think about this and I'm like, well, the problem here is that hashes are deterministic. If I hash the same thing twice, I get the same password output. I do want to keep that they're deterministic. I don't want to switch to something different. I don't want to introduce randomness, because if I introduce randomness, I can no longer verify passwords. But I can do something pretty clever called salting a password. And so here, the idea is I'm going to associate with each user a unique value in addition to the password. So for example, for each user, instead of simply storing, this is their username, so Alice's password is, and then I hash their password, I'm going to say, this is Alice. This is the random value associated with Alice. And instead of just hashing their password, I'm going to hash the password and the random value unique to Alice. No one else is using this random value. Only Alice is using that random value. Okay, so how do I verify then if someone sends me their password? Well, then all I have to do is take the password that the user sends to me, concatenate it with the salt that I'm storing, the random value associated with Alice that I remember. I hash both. I check the resulting hash against the one that I stored. If they match, the password is correct. Otherwise, the password is incorrect. So do note here that the salt, it has to be actually stored. I have to remember what the salt is, because if I don't remember what the salt is, how can I recompute this hash? So I store, this is Alice, this is their salt, and then this is the hash of Alice's password combined with their salt. Okay, so I do need to store the salt every single time. It's not a secret value. I don't really care if the attacker knows. The important thing is that it's different per user. And does this solve our problem from before? Well, think about what happens if two people sign up with password 123 as their password. Well, the first person is going to say, this is Alice. This is their random value belonging to Alice that's unique to Alice. And the hash is password 123 plus Alice's random value. That is some hash output. What about Bob? Bob signs up with the same password. Here is Bob. Here is Bob's different unique random value. Here's the hash of Bob's password, the same thing, concatenated with Bob's unique value. So now, even if two people have the same password, the hashes are going to look different, which is good. Right, so now we have Alice, and then, I don't know, the salt of Alice, and the hash of the same password concatenated with Alice's salt. Same thing for Bob, but Bob's password is going to be concatenated with his salt. So those values are different. Okay. So questions about how do you generate salts? That's a good question. The important thing, the property that we really care about is that it's different per user. That's the main thing that I care about. So you can generate salts however you want. You can do them randomly, but the important thing is that they are different per user. That's what we care about. And do we care about salts being secret? Well, not really, because if someone knows the salt, what can they really do? The salt doesn't help them learn the password. The salt doesn't help me reverse the hash. The salt isn't the password. You can't enter the salt and try to be logged in. So the salt itself is not supposed to be secret. Okay. So one good thing is that now the attacker doesn't know whether or not two people have the same password. But there's another really good benefit, which is, remember those dictionary attacks? Those become a lot harder now. So for example, think about what happens if a user wants to do a dictionary attack and learn everybody's passwords. What would they do? They would take their dictionary of like the 10,000 most common passwords. They would hash the first one, hash the second one, hash the third one, compute this big list of the hash of all the common passwords. And all they have to do now is be like, Alice's password hash is this. Check their lookup table. Alice's password is this. And here's Bob's hash password. I check the lookup table of all the hashes that I compute. I figure out Bob's password, and I do this over and over again. So the only brute force work that I had to do in my initial approach, I only had to hash the dictionary once. I get the hash of every single possible password. And then for each user, I check their hash against the ones that I computed, see if I find a match. And if I do, then I know the user's password. So the total runtime for this thing is I need to hash all the possible passwords, which is like O of n. And then I need to check one user per database, which is like O of n. Okay. So in essence, the total number of things that I had to hash was just the entire dictionary one time front to back. I read the entire dictionary front to back a single time, hash it all, I'm good. Okay. What about the salted version? Well, think about what has to happen now. So suppose I do the same thing. I go through, I hash every single thing. I hash, password 123. I hash password 1234. I hash every single common password I can possibly think of, all the dog names, all the birthdays. And what do I do now? Well, I look at the first person's password, which is password concatenated with Alice Assault hashed. And I go to my table hoping to look it up, and wait a minute, my table only has all of the hashes of passwords, but I want to find a match, or I want to be able to like find the input that gives me password concatenated with salt. So these two are like not compatible, right? If I want to know Alice's password, I cannot go to my table and try to find it because the password was hashed with the salt, and all the ones that I computed did not use the salt. So as the attacker, I'm now in trouble. How do I actually figure out what the correct passwords are? I need to do a little bit more work. Specifically, instead of just going through and hashing every single value, password 123, all the birthdays, I actually need to say, I'm going to take every value in the dictionary, concatenate every single value in the dictionary with Alice's salt, and then hash all of those and get a lookup table. And who is that lookup table good for? Like, who can I attack with that lookup table? Only Alice, because that lookup table involves Alice's salt and is specific to Alice's salt. Now what happens if I want to learn Bob's password? All of those hashes that I concatenated or computed using Alice's salt are worthless. So back to the drawing board, I have to rehash the entire dictionary using Bob's salt concatenated at the end, and then check again. And if I want like David's password, I have to go back, hash the entire dictionary again with David's salt, and check against David's hash password that's stored. So now, instead of hashing the entire dictionary once for every single user, I have to hash the dictionary once for the first user, rehash it again for the second user, rehash it again for the third user. So my brute force attacks just got harder by like a multiplicative factor. Instead of hashing once for all the users, I have to hash once for every single different user. So now the attacker's life is harder. So adding assault, it's a cheap way to make the attacker's life a lot harder. Okay. Any questions? There's a couple chat messages. There was a question of, is it possible to dehash? Remember, hashes are one way. So you cannot take the output of a hash and learn what the input is. Hashes are one way. That's the property that we talked about. There was a question of, does the attacker know which hash function I used? Did I use MD5? Did I use SHA-1, SHA-2, SHA-3? Well, you could try to keep that secret, but remember, we assume the attacker knows the system. So yes, I could try to keep the hash algorithm secret, but in general, we assume the attacker knows the system. And in practice, there are just not that many hash algorithms to choose from. So the attacker probably knows. There's a question of, do I need to hash the username? You don't really have to. The important thing here is that I want passwords. I want the brute force attacks to be harder. So adding the salt did that for me. Question of how do I generate salts? Random is okay. Okay, they just have to be different. Okay, that's one possible fix to all of my problems. There's a second fix, and this one almost seems kind of backwards at first. And it's like flying in the face of all the things we've talked about in cryptography. So for once in crypto, we finally want something slow. And like, wait, why would I want something slow? And why would I want to go against all the common wisdom of like, we want algorithms to be fast, we want people to be able to use the algorithms. Well, think about this. When someone wants to log in, how many hashes do you have to compute for the user who wants to log in? One, right? The user gives you a password and you hash that one password, check if it's correct or not. Okay, maybe the user has to try a couple times, they forgot their password. That's still what, like 5 hashes, 10 hashes? It's not a lot. And so for a user who is just logging in legitimately, taking like 1 try, 3 tries at the password, they are not going to notice a difference if your hash takes 0.0001 seconds or 0.01 seconds. They're just not going to notice from the user's perspective. But now think about the attackers. What is the attacker doing? The attacker is computing the hash of not just one thing, but the entire dictionary of thousands and thousands of values. So if we make a hash like 1,000 times slower, guess how much longer the attacker's brute force is going to take? 1,000 times longer. Or if I make the brute force, or if I make the hash like 1,000,000 times slower, now the attacker's time is going to be 1,000,000 times as long. True, the user's time is also going to be 1,000,000 times as long, but for the user who's only hashing one thing, they are barely going to notice the difference. It's the difference between like 0.1 seconds and 1 second. They're not going to notice. But for the attacker, it could be the difference between like 1 day and 10 days. So there could be a really big difference for the attacker, but a small difference for the user. So here, we're not actually affecting like the asymptotic difficulty. We're not doing big O of anything. All that we're doing is we're adding a big constant factor, which users who only compute one hash will never notice, but attackers who are computing tons and tons of hashes, it's going to make them really miserable. So that's the idea behind slow hashing. Okay, there is a slow hash you get to use in project 2. Here's some information about it. We'll talk about it more in the project as well. It turns out slow hashes for passwords are really useful. You can even use the output of the slow hash as a key. That's what this function does for you, which is kind of cool. So if you take the user's password and you hash it using one of these slow hashes, the output is actually usable as a key because it's a random unpredictable value. So that's kind of cool. Okay, but more on that in project 2, promise. Okay, so final thing I'll talk about password hashing before we move on is there are 2 types of attacks when we talk about password hashing. And honestly, sometimes it's easy to confuse one with the other or like believe that they're kind of the same thing. But if I tease them apart, you'll notice that like they're actually quite different. So one of them is called offline attack and one of them is called online attack. So I guess we can start with online attack because that might be the one that seems most natural. So in the online attack, how would I try to brute force? Here's what I'd do. I'd go to the website and I would type in username Alice, password 123, and I would hit the submit button. And if I hit the submit button, who is computing the hash? I send it to the server. The server is the one computing the hash, checks against their file. It doesn't work. And they return to me and say, sorry, password's wrong. Try again. And I'm like, okay, username Alice, password 1234, submit, send this into the server. The server computes the hash, checks it against the password in the database. No match. So they reply to me saying, wrong password, try again. Okay, password 12345, send it over, server hashes, send it back to me. So here in the online attack, I am interacting with the service. So in other words, I am making the server do all the work. I am submitting all these password guesses and I'm making the server do all the work, compute it and send it back to me. And if this word online doesn't seem like super intuitive, you can almost think of it as what did I have to do here? I had to log onto the internet and like send all these requests over the internet, make the server calculate it, and the server tells me that I'm wrong over and over and over again. So that's the online attack. Here, I am making the server do all the hard work of hashing for me, and I am simply entering tons and tons of guesses. So that's the online attack. These tend to be pretty slow because what does the attacker have to do? They have to submit all of these to the server one by one and wait for the server to reply, which could be slow. So these tend to be kind of slow. These are also a lot easier to defend against because how do you defend against it? Well, with timeout or something, right? If the user gives you the wrong password 10 different times, like lock them out. Don't try again for another hour or something. Now the attacker's life, when they want to brute force millions and millions of possible passwords, is a lot harder. So that's the online attack. That is me typing in passwords over and over again and making the server check. Okay, by contrast, there's something called an offline attack. And here, we are not going to ask the servers to do the hash. We're going to do all the hashing ourselves. So the most common example here is that we steal the passwords file. So we now have a list. These are all the users. These are all their passwords, salted or not, doesn't matter. I have a list of all the users. I have a list of all the passwords. So now who gets to compute the hashes and check if they match? I can do it myself. I don't have to ask the server to check for me. Hey, is this password right? Is this password right? Is this password right? I can do all the checking myself by computing the hashes. So this is called an offline attack. If you don't like the name, you can think of it as once I steal the passwords file, I no longer need to connect to the internet or do anything. I can take the passwords file. I can go to my like remote cabin in the wilderness and I can compute password hashes as much as I want and learn people's passwords without ever talking to the server again. So that's the offline attack. And offline attacks are usually a lot more dangerous because the attacker can try lots and lots of different passwords, and the server kind of has no way to stop them. If you have the passwords file and the attacker goes and buys a ton of compute power, like tons of processing units, and computes tons of passwords in parallel, there's nothing the server can do to stop it. It's an offline attack. How do you stop these? You have to use the defenses from before, where you salt the password, make the attacker's life a lot harder. Now they have to compute the dictionary once per user, use slow hashes. That multiplicative factor of 1,000 is really going to make the attacker's life a lot harder. But in general, offline attacks are a lot more dangerous than online attacks. So it depends on your threat model. If you're worried about online attacks, maybe your password doesn't have to be the strongest thing in the world if you assume the server implements like a timeout or something. But if you're trying to defend against offline attacks, you need a really, really good password because the attacker can hash as much as they want and check against your guess or check their guesses and make sure they're correct. Questions?
Yeah, so I know that most like logins actually let the user change their password when you press it. Oh, for all password, you can change it in like email. Isn't that like kind of bad security because if you tweet your email and you change any other password?
Yeah, there is a good question, which is what about those like forgot my password things? I don't think it's super relevant to this lecture or like the hashing part of it, but you are right that there are often like side channel attacks where instead of trying to break the password itself, you maybe like try to trick the server into sending the forgot password link to you or something. So those are totally possible. But in terms of like trying to just defend against leaking the password itself, this is kind of what's considered state of the art. It's a good question though. There's lots of other social engineering ways to get around stuff like that. Okay, cool. So quick summary of password hashing. So we talked about how encrypting the password is not a great idea because the attacker can steal that and decrypt the passwords. Storing plain text passwords is a really bad idea, but hashes are great because you don't have to keep the password yourself, but you can still verify that the passwords are correct. So even if someone compromises your system, they cannot learn all the passwords. How do attackers try to break this? They use brute force attacks. How do I stop that? I add a salt. I make the hashes really slow. And we also talked about how there are two categories of attacks. Okay, cool. That's it for password hashing. So I now have time to tell you all about these random side channels and case study stuff. So I'm going to do that until we run out of time. Okay, so first one I'll talk about is something called a side channel attack. Now these are really cool. And these attacks are actually also really common. And so here, the idea is that we're not going to like, I guess maybe another way of framing this is you might have a scheme that is perfectly secure. Some like genius PhD wrote a paper and they proved, yes, HMAC is secure. Or you're using like AES, never been broken in 1,000 years or whatever, like won the competition, everything. You could have a scheme that is in theory perfectly secure. But if the way that you implement it, the way that you write the code to make that thing work is even slightly off or flawed, you could break the entire scheme. So yes, the scheme could be totally secure in theory, but the way that you implement it could cause problems. And so that's really subtle and something that is like really, really dangerous when it comes to implementing cryptographic schemes. A lot of problems are broken because not because the scheme is insecure. Like, yes, we know AES is secure, but if you implement AES insecurely, now you're going to have problems. So let's see if we have examples of side channels. I don't know if this one's super useful, but the one that I really like about side channel attacks is like something like timing attacks. So I'll give you a really quick example, which is think about how someone might check if a password is correct. So I know this is not how people actually store passwords, as we just saw, but imagine if someone or some server wanted to check if your password is correct. So what would they do? Well, I would imagine they would take my input and compare it to the password that's stored. So if Alice types in a password like what's Alice's password? Give me a guess. Don't give me your actual password. What is it? 1234. Okay, really secure password. So if Alice sends a password like 1234, then we're going to compare it against the 1234 that we stored. So what are we going to do? We're going to compare. Okay, the character 1, yes, the same. The character 2, okay, yes, the same. Character 3, the same. Character 4, the same. And now that I checked that they're the same, I know Alice's password is correct. I log them in. Okay. But what if someone gives a password that's totally wrong? Like Alice's password is 1234, but the password that I give is like, 5555 or something. It's totally the wrong password. So what might you do? You might start comparing. You compare 5 and 1. Oh, those are not the same. These two values are not equal, so I can immediately tell you that the password is wrong. Okay. What about if I gave a password guess like 1235, which is closer, Well, what would I do in this case? I would check 1 and 1, the same, 2 and 2, same, 3 and 3, same, 5 and 4, not same, return false. So yes, in theory, this works perfectly fine. Like if you think about just in theory, I check if these things are equal, perfectly secure. But like think about the amount of time it would take to do the top thing versus the bottom thing. And think about how an attacker could be able to leverage that. If the attacker sends both of these incorrect passwords, then maybe if your scheme is really insecure, what if this one on the bottom returns in like 1 second because you immediately find out that the password is wrong and it returns false? But what if this one on the top takes like 3 seconds to return because it has to check the character 1 and then the character 2 and then the character 3, and only at the 4th character does it notice that something is wrong? That one at the top is going to take more time to return. So maybe even though my scheme is perfectly secure in theory, what would this look like in like a cryptographic paper? It would say something like compare A is equal to B. If it's true, return false, whatever. So in theory, it might be perfectly secure, but the way that you implement it, you might end up leaking information. An attacker might know, hey, my guess of 1, 2, 3, 5, that was a lot closer because the code checked a bunch of characters before returning the first wrong one. But the one on the bottom, that one returns so quickly that it was probably way off. So maybe that could be something that an attacker could use. That's called like a timing attack, where I take advantage of the timing of when the values are returned to me or when the results returned to me. So not something you have to know in like great detail, like it's kind of a made up example here. And yes, in real life, most people are not going to notice a difference between like, 1 character comparison and 3 character comparisons. But it turns out these kinds of timing attacks, they do happen in real life. And the amount of time that it takes for you to compute something, even that can leak something. So you have to make sure you can't even leak things in the amount of time it takes you to compute a result for the user. So it's really tricky. Okay, cool. So that's a really quick example of side channels. Apparently this happened in like some spy setting or something, but there you go. Okay. So that's our first special topic checked off. I'll try to get through some more since we have some time. Okay, this one's really cool and has a really funny name. It's called Nothing Up My Sleeve Numbers. So in this one, we're going to notice that cryptography uses a lot of constants, like constant values. So here are some examples. Like the SHA algorithm, the way that it works, the hashing algorithm, is it first initializes something like k equals 150, constant value. If you look at the code of the algorithm, there is a hard-coded number in there. It's probably not actually 150, I made it up, but it's some constant value, hard-coded. There are some other ones, like in Diffie-Hellman. Everyone uses the same P and the same G. It's a public constant value that everyone can know. Or think about like elliptic curve, Diffie-Hellman, those also have constants that everyone has to know. In the HMAC, do you remember like the iPad and the OPAD? Those were constant values that were just written on the slide. They were constants. And so in a lot of these cases, like lots of different values would work. Like if you took the HMAC and you swapped the values of iPad and OPAD, maybe the security proof is still okay. But when I'm publishing a paper or when I'm implementing HMAC, I have to choose something. Even if any value works in theory, I got to choose something. Or like in Diffie-Hellman, any prime P and any generator G works. But when I'm actually using Diffie-Hellman in real life, I have to pick something. So what do I pick? Right? Like the P and G, what do I pick? What's the default P? What's the default G? What do people use? So one question that you might want to ask if you're trying to be a good cryptographer and you want to be really paranoid and check things is, who chose these numbers? Where did they come from? So as an example of why you have to be really careful about this stuff, here's a bad PRNG from back in the day. And so, it's like a really weird PRNG, it was really bad. And in particular, this PRNG, when it was published by the NSA, the security administration or whatever, like the US government, they published it with these 2 hard-coded parameters. So in their paper or in their implementation that they released to the world for use, they said, please set P equal to this specific value. And please set Q equal to this specific mysterious hard-coded value. So like, please set Q equals 1723, blah, blah, blah. And so a lot of cryptographers saw this and they were like, okay, but how did you pick those values? Like any value would have worked here. So why did you pick 17 something, something, something? And so it turns out like later people ended up figuring out, like I'm not going to read this all, but people ended up figuring out that those numbers that were chosen were actually specifically chosen so that it gave the NSA like an advantage or like a backdoor into the system. By backdoor, I mean that those numbers were specially chosen so that they had a way of breaking the security of this scheme that other people didn't. So, ooh, scary. I think this is not actually confirmed. So, I don't want to I don't want people knocking on my door. So it's allegedly true, but apparently people tend to believe that this actually did happen. And so what ends up happening is that because of those specifically chosen numbers, apparently the designers of this algorithm knew that those specifically chosen numbers allow people to figure out what future output is or past output of the PRNG if you know the secret trick. So they specially chose numbers to give themselves the advantage of they can decrypt things or they can break the PRNG. But from other people's perspective, they were like, it's just a number. What are you talking about? I just chose the number at random. But they knew they didn't choose it at random. They chose a special number that gave them a way to break this PRNG. Okay, so if you're in the market for a PRNG, please don't use this one. Apparently the NSA rigged it, so don't use it. Okay, okay, slide's broken. The NSA hacked me already. Okay, there we go. So this happens kind of all the time. There are lots of different cases like this. In fact, something pretty funny is that when you're using Diffie-Hellman, there are proofs out there that certain values of P make it a lot easier to break Diffie-Hellman. So even though any value works, there are some values that are a little bit more secure and some values that are a little bit less secure, depending on which value that you choose. So which of those values was chosen by everyone in the real world who uses it? I don't know. Where's this modern P come from? I don't know. Nobody knows apparently. So kind of mysterious. Okay. And so the problem here basically is that because of the fact that sometimes specially chosen values can give you backdoors, there's kind of a problem here, which is that when you publish one of these schemes or when you publish an implementation, it is true that in theory, any number would work. But when you choose any arbitrary number, you might get people suspicious, even if you are not actually trying to be nefarious or evil and trying to insert a backdoor or trying to choose a value that makes the scheme less secure, people might still be suspicious. They might ask you, hey, your implementation uses this hard-coded value. Where did you get it from? And so, yes, there are stories, lots and lots of stories, but basically the idea here is that if you would like your implementation or your system to be good, you should always be transparent about where you got these numbers from. So ways to do this, for example, for example, do not do what the NSA did. And when people asked, hey, where'd you get those numbers from? Any number would have worked. So why'd you choose this really specific one? And they were just like, I don't know, chose it at random. That will make people very suspicious of you. However, you can do things to make your schemes more transparent. So here, we're not talking about whether the scheme is secure or not in theory. We're talking about whether your implementations are transparent and are successful at convincing other people that you're not doing anything suspicious. That's why it's called nothing up my sleeve numbers. We want to be able to convince people that these numbers were not specially chosen to do something evil. Okay, so examples of how you can do this. One thing you can do is you can simply argue and give an actual reason of why those numbers are good. So for example, when people design AES, they said, yes, any number works here, but I chose these because they have this nice property that they're going to be harder to break. So they gave an actual cryptographic reason, people believed it, so nobody suspects that AES has a secret backdoor because those numbers were clearly argued. Okay. Other ways of doing it are, you could also pick something that has human significance. So for example, you can choose your birthday, your name, the digits of pi comes up a lot. You can choose values that are 1, 2, 3, 4, 5, 6, 7, 8, 9 or something. So if you choose values that have obvious significance, then here you're not just saying oh, I pulled the value out from nowhere. You can say, I chose these values because anything would work. So I picked something silly like digits of pi or my name or my birthday. And here you might be like, but what if your birthday is the backdoor? Well, yes, that's technically possible. But in general, coming up with these really specific values that cause backdoors to exist is pretty difficult and usually requires, trying millions and millions of values. So in general, if someone has something transparent like this, you can probably believe them and know that, yeah, the first few digits of pi, that probably is not coincidentally the secret value that makes things break. So again, being able to argue this, it also does involve things like human factors. How do you convince other people that your algorithm is safe? But in general, you have to be careful because if you choose any old number when any number would have worked, cryptographers are very paranoid people. They will always come up to you and say, please tell me how you chose these numbers, because maybe you chose them to give yourself an advantage, and we don't like that. Okay, so that's nothing up my sleeve numbers. Since we're kind of short on time, I will not talk through all these slides, but if you're curious, Nick Weaver, who used to teach these classes, by the way, you can start backing up if you want. Nick Weaver, who used to teach these classes, had a whole section on like iPhone security. He had like half a lecture on it. So if you go back to past semester websites, you can watch them. It's kind of cool. I'm not going to talk about them because it's a lot of words, but Apple apparently put a lot of thought into this. So we have some summaries over here. Kind of cool. None of this is in scope, obviously. One that's kind of cool is that you can now become a better consumer of cryptography. And I'm not going to talk about this either, but turns out now that you know what the established protocols are, you also know when people are feeding you bullshit, which is really great. So if someone comes up to you with like this huge scam, now you know what the accepted protocols are, and you know when people deviate from those protocols, they are often selling you crap. So that's a pretty good advantage now. There are examples, and there's literally a slide where Nick is just like tweeting at people angrily about things. So you can read that if you're curious. But again, none of this will be in scope. It's kind of interesting. Okay, so that's it for the crypto unit. Good luck on your midterm, everyone, and I'll see you next week. Okay, bye-bye.